I'll do 10, 11, 12 in one video because they all deal with these Minitab outputs. So this Minitab output is just a way of displaying statistical tests, displaying statistical calculations, something like SPSS, something like when we do tests in the TI-84, TI-83 calculators. So these Minitabs are showing us the results of hypothesis tests in these three questions. All this information here up top, it's telling us the null and alternative hypotheses. So it gives us step 1. The test of mu equals 60 to mu does not equal 60. Well, let me write that better. It's giving us the null hypothesis is mu equals 60, and the alternative hypothesis is mu not equals 60. What else does it give us? It gives us the assumed standard deviation. That's sigma. N, it gives us the mean, right? This is the sample mean. The standard error of the mean, right? That's that sigma divided by the square root of n. It gives us the 95% confidence interval. This might be different. It might give us 99. It might give us 90, 98. But this is the 95% confidence interval, where we're 95% sure that the true population mean is between these two values. A little off there. Strange. It gives us the z-test value. And it gives us the p-value. So we can make our decision using either the traditional method with the z-test value, and we find the critical value, or we can use this p-value with alpha. So the answer to the question is, what's the p-value? Well, the p-value is right there. The p-value is 0.001467. That's the p-value. And if that p-value is less than our alpha level, whichever alpha level we're considering, reject the null hypothesis. P-value is greater than alpha. Do not reject the null hypothesis. Let's see if that comes up. Number 11. The following output, again, Minitab. So let's start here. So the test is, null hypothesis is population mean, mu is 33. Alternative hypothesis is the population mean is not 33. Cool, we've got n, we've got the sample mean. Again, here's sigma. Sigma divided by the square root of n. Okay, sigma divided by the square root of n. 95% confidence interval again. We have z and we have p. Z-test value, let's write that. And the p-value. I don't have birds, but there are birds outside that chirp and, bring greetings every morning. So those are the birds that if you're hearing them, I'm almost sure you're hearing them. These birds in the background are not I guess they are my birds because they're outside my window, but they're out there. Okay, cool. So that's our null and alternative. So the question is, do you reject the null hypothesis at the alpha equals 0.05 level? The simplest way to do that, there's two ways to do that really, right? There's the traditional method. And then there's the p-value method. I'll show both, and you'll tell me which one you find more simple, more effective here. So the traditional method, and again, I can go from the formula sheet, right? The second step of the traditional method is to find the critical value. So step 2, that's where they diverge, right? The first step is the same, state the hypotheses, identify the claim. But for the traditional method, the second step is find the critical value. For the p-value method, the second step is compute the test value, which is the third step here. So they differ. So let's go with the traditional method. Let's find the critical value. To find the critical value, we need alpha. Alpha is 0.05. And this test, if I was to draw what it would look like, it's two-tailed. Why is that? Because the alternative hypothesis is the population mean does not equal 33. And the birds have stopped since I've spoken about them. I wonder if they can hear me, understand what I'm saying. So because the population mean does not equal 33 is the alternative hypothesis, it can be greater than 33 or it can be less than 30, as long as it's different from 33. So this will be a two-tailed test. If it was just less than, it would just be one-tailed. If it was greater, just greater than, it will be one-tailed. But since it's not equal to, it can be less than or greater than. So this is two-tailed, right? So so alpha is 0.05, two-tailed. This is a z-test. I know that because they give me the z-value, not the t-value. I also know that because I have the population standard deviation here, right? The assumed standard deviation. Okay, so this is going to be a z-test. So I'll say more. As opposed to if you look at the next, if I leap forward to the next one, you see I don't have the standard deviation here. I don't have the population standard deviation here, the assumed one. And they give me the t-value. This is going to be a t-test. Right? Okay. Okay, so alpha is 0.05, two-tailed. Again, I'm going to go down to the t-table because it gives us nice information. Alpha is 0.05, but wait, two tails, 0.05. Right? Don't look at the one-tailed 205. This is a two-tailed distribution, and alpha is 0.05. So now go all the way down to the bottom. 1.96 is my z-value. See, two-tailed. All right, two tails. Alpha is 0.05. 1.96 is my z-value. So I go back here. This z-value here is 1.96. And this z-value here is negative 1.96 because this is all symmetric about my mean in the center there. Mean is 0. Okay? So that's the second step. Critical value equals plus or minus 1.96. The third step is to calculate the z-test value. Normally we would use a formula to do that, but since this is a Minitab output, we have the z-test value, negative 3.04. Now this z-value, this is the test value, right? So this is the value we're using to test. If that test value lies in either of these two intervals, this is rejection, this is rejection, this is non-rejection. If that test value lies in any of these two regions, reject the null hypothesis. If it falls between negative 1.96 and positive 1.96, if it's here, don't reject the null hypothesis. So what's our decision? Negative 3.04 is definitely somewhere over here, right? Right? It's in the rejection region. Thinking about this as like a number line. It's not here. It's over there. So because it's in the rejection region, reject the null hypothesis. And that's the decision. That's the answer to the question. Do you reject HO? Yes, you reject HO. You reject the null hypothesis. That's the traditional method. Those are the steps involved. Now the p-value method, check this out. Here's what the p-value method says. If p is less than or equal to alpha, reject the null hypothesis. Or, if p is greater than alpha, I want to write do not. I don't want it to look like do not. Do not reject the null hypothesis. All right, so here we are. So here's our p-value. P is 0.002355. Alpha is, right, 0.05. See, we're comparing that position, right? That second position. See that? See, that's a 5 versus a 0. So the p-value is definitely less than alpha. And if it's less than equal to, the decision is reject the null hypothesis. You can use either method. They'll both work. I think the p-value method gets you there quicker, but the traditional method is also important to know as well. Either way, the decision is reject the null hypothesis. All right, number 12. Here's the output from a hypothesis test for a population mean mu. I'll start off the same way. Step 1 of the process. Null hypothesis is mu equals 47. Alternative hypothesis is mu does not equal 47. It's not always not equal to, but just these 3 examples were. Fine. We don't have that assumed sigma there. We don't have the population standard deviation. Sigma, 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 sigma. We don't have that. I do have my sample mean. I have my sample standard deviation. I have the standard error of the mean. In this case, it's S over the square root of n. I have the 95% confidence interval. And I have the t-test value and the p-value. So this question is asking, because it's a t-distribution, a t-test value, we have degrees of freedom. When we're looking at this t-distribution table and we're finding t-values, we need degrees of freedom in order to do that, to find those critical values. Degrees of freedom. How do you find the number of degrees of freedom? Is it on the formula sheet? Might be. This is chapter 8, I believe. Yep. Hypothesis testing. So a t-test, here's the formula to find the t, to compute the t-test value. But there, we've already done that. The Minitab gives us that. Here's degrees of freedom, df. Degrees of freedom, n minus 1. So the degrees of freedom is 53 minus 1. So degrees of freedom, we have 52 degrees of freedom here. And I got n from the Minitab output. So that's the 3 of them.